This is an updated version on the lecture of field of vision. Now we check if the field is normal or abnormal. This is the numerical numbers. As you can notice here, the locations are not in the central area, are very close, not regular as in case of the Humphrey. Keep in mind that we cannot compare values of the two machines because they are not in the exact locations, and also the decibel we see here, it's a log value, and the base of the log is different between these two machines. If you need a full understanding of this point, I recommend you to check the second presentation titled Visual Field Sensitivity is a Log Value, and a link will be written down in the description. Grayscale is an interpolated map. It's a probable or likely map. Only discrete number of locations are tested. There are large gaps between tested points for which no information is available. These gaps are filled with probable or likely information. Actually, we test 50-something or 70-something points, and the software uses 2000 symbols to print out such a grayscale. This grayscale gives us an impression, but not a real thing to depend on. We can use this grayscale to explain to the patient what we want. Notice here that the grayscale gives us an impression as if there is upper arcotoscotoma and there is nasal stop. But if you check here in the pattern deviation, such things is not seen. Also here, the grayscale gives us an impression of a lesion, which is not the case down here. So actually we have to depend on the pattern deviation for interpretation of possible local changes in the field. Another example with changes shown here in the grayscale, nothing is seen here in the pattern deviation. Next, you need to check for the total deviation, pattern deviation in case of Humphrey, or comparison, corrected comparison in case of octopus. Here the total deviation. These are the recorded patient sensitivity. The software starts to compare each point with the normative data already stored in of the same age. So for this patient, the normative data for this point is 32. So the difference is written here, it's -5, and so on. Each point is compared with the corresponding point of the normative data of the same age, and differences are recorded here. This is higher with 1, this is below 3, and so on. Why you are comparing with the same age? Because the sensitivity decreased by half to 1 decibel per decade, so we have to compare with the same age. This is the importance of being sure that the date of birth is correctly added to the machine at the beginning of the test. So the total deviation is the difference between the measured thresholds of each individual test location and the age-corrected normal value of that location. Then under it, the numerical part, we have this graphic probability plot. The sensitivity of each location in the normal population was tested to draw this frequency distribution curve of sensitivity of that location. For example, in a normal population, a value of 20 decibels was found in 10 patients, 22 decibels was found in 20 patients, 24 was found in 60, 26 was found in 20, and so on. So we have this curve. Now, once we have this curve, we know what is the probability of having any of these values in the normal population. For example, this value occurs in 5% of the normal population. This value occurs in 1%, in 0.5%, and so on. And this is the clue we have in the graph. Now, if our patient one location get a value of 17, then the software will start to compare it with the normal population, and 17 looks to be low, but this value occurs in 0.5% of the normal population. So we have this mark. So this sign means that this point is of a low sensitivity, but this value can occur in 0.5% of the normal population. This value is low, but it can occur in the 5% of the normal population. So in other way, we can say that these points, almost all of them except these two, they are looked to be depressed. But we can be wrong in our assumption by the probability 0.5% or 1% or 2% or 5%. These values can occur in the normal population with these values. The second part here is the pattern deviation. Again, we have values, numbers here, and probability plot down. The pattern deviation, it is an adjusted threshold. To understand the idea behind this, let's consider we have a patient tested. We get the values of all the test locations and we arrange these values from the highest to the lowest. Suppose this patient get some cataract over the next years. The opacity will reduce the amount of light entering to the eye, and the sensitivity of all these points will be universally depressed year after year with the same amount of depression. On the other hand, if our patient has glaucoma, we know that glaucoma affects certain areas of the retina gradually till everything is affected. So every time we test the patients and we get the different values and we're going to arrange them from the highest to the lowest, always the lowest will be here at the bottom, regardless its anatomical location, but on this arrangement it will be here. So as the glaucoma increases over the time, the damage will be shown here in the bottom, and gradually more and more locations will be included. Suppose our patient developed both glaucoma and cataract at the same time. So over the years, cataract will affect the sensitivity of all the areas universally, while glaucoma will affect some areas, and gradually more areas will be affected, and by the end everything will be affected at the end stages of glaucoma. So if you want to get rid of the effect of cataract, this is the idea. Now here is shown the normal values of that age, arranged from the highest to the lowest. If we go to the location 85% and compare the numbers of our patient to the normal, the difference here is 2. This time the difference is 4. At this time the difference is 16. So every time we make such a comparison, and the difference will be added. So this way we are going to reduce or remove the effect of cataract. This process wouldn't affect the results on glaucoma, because the receptors are involved in glaucoma are away from the location 85%. So the idea why they choose the location 85%, just to keep the affection of the glaucoma to the very end stages. But at the very end stages, when the glaucoma reach to the location 85%, this process will affect the glaucoma as well. So the software simply will arrange the values of the patient from the highest to the lowest and compare them with the normal of that age and start to see the difference. For example, in patient number 1, the difference is 3 between our patient and the normal. So this 3 will be added to everything. All these values will be elevated by 3. In the second patient here, the difference is 10. So the software simply, here the patient is higher than the normal. So the software will reduce everything by 10. So it's something programmed. Just arrange the values of the patient from the highest to the lowest, compare them with the arranged values of the normal age, go to the location 85%, and the difference will be added or subtracted depending on the values. So the software just adds things or remove things depending on the difference between the 85% location value of the patient to the normal. This way, all the time we are going to remove the effect of cataract, and nothing will be affecting the glaucoma except in the late stages of glaucoma. So notice here, this is the total deviation. When compared to the normal, you get a value -5. This is the patient value 27. The normal is 32, so the difference is -5. But when doing adjustment, the 27 became 28. Now, removing the difference between 28 from 32, the value here is only -4. So all these values are adjusted depending on the location 85%. So here we have the pattern deviation, and down here we get the probability plot again drawn. So pattern deviation, it is the difference between the adjusted threshold, adjusted depending on the difference at location 85% with the normal. It is the difference between the adjusted threshold of each individual test location and the age-corrected normal value of that location. This process will adjust things either up or down. It is just something going on regardless what are the values. The idea is to get rid of the generalized effect of media opacity. Here the probability plot drawn. In this graph, this is the normal. The white part here is the patient sensitivity. In this area, you can see that our patient is generally depressed. The field is depressed than the normal, but also there is a localized changes here. So if you apply the process we have just done, then we could take rid of the generalized depression and keep the local changes apparent. So we are accustomed to say, if we have changes here, these changes are due to generalized depression, then after making such adjustment, changes here are localized changes. This is correct in most of the cases, but not in every case. Okay, let's see this example. If you look directly here, we will apply the rule. Yes, we have generalized depression and we have localized changes here. But actually, this patient is a young patient, was in the 20s. She got clear media, and at the same time it was an end stage of glaucoma with marked affection of all the sensitivity all over. As you can see here, the values, most of the values are 0 except for a couple of values here. Only we have here 2-3 points, and everything is in the range of 1 or 3 or something. So on doing the adjustment, the location 85% was included. So after doing the adjustment, everything was. So you have to be careful. Not all the cases have got the same meaning of generalized changes, localized changes. No, sometimes if the affection of glaucoma is so advanced, you get a mistake of this appearance. Now, keep in mind again the example here that in case the position 85% is high, everything will be depressed. If you look here, you will say, yes, we have generalized depression, no localized changes, and on this eye, yes, generalized depression and localized changes in the periphery. As you notice here, all this, the peripheral part is 0, and we have values here. This goes with the pattern deviation. But on this eye, the zeros are not shown here, simply because the zeros reach to the location 85%, and the adjustment let everything disappear. So don't be mistaken to say every time you see this appearance, this is generalized, no localized. No, this is not the true in every case. You have to check all the field, and also you have to check the patient to make sure that there is no media opacity. Again, because of the problem of such an adjustment, in the Humphrey, when the sensitivity, the mean deviation reached to -20 decibel, the software stopped printing the pattern deviation altogether to avoid such a mistake. Again, if the position 85% is higher than the normal, then everything will be reduced. As in this example, this field belongs to a child 11 years. He was happy trigger patient, and the values here are very, very high. As you can see, you have values like 63, 59, things like that. So comparing, everything is normal here, but on making the adjustment, the position 85% is very high, so adjustment changed everything to be very low. Then we have these points as if there is a fraction localized. But of course, this does not follow our principle. No way to have localized changes while nothing is shown here. If pure localized changes are there, again, it must be shown at the same location here. Just I'm putting this to show you that the software just adjust numbers, go to location 85%, check the difference, and this difference can be added or subtracted of all the values of the patient. Then comparison is done again. In case of octopus, it's called comparison and corrected comparison. So here the sensitivity of the different locations are compared with the normal, and a plus sign written here indicates that this location has sensitivity within the range of 4 decibels of the normal person. And down here we have the probability plot of these points. Again, similar to the Humphrey, we have here corrected comparison. But the corrected comparison is calculated in a different way. The deviation from the Bebe curve is subtracted from the defective value to show hidden localized defects. To understand this, let us see what's the Bebe curve. The Bebe curve is comparing the deviation of the different locations from a normal person, and these points are arranged here on this curve. Number 1, 2, 3, 4 on this end we have small defects, while on this extreme end we have large defects. The blue zone here, this is the normal curve. So the patient's recorded value are deviated from the normal. This point shows a deviation on the y-axis of up to 4, that's why it's written plus. All these plus locations are arranged here. And gradually the rest of the locations are arranged in such a way that small defects are on this side and large defects are on this side. So this curve depends on the deviation from normal. It doesn't take in account the actual locations of the point. So on this side we have the smallest values, and on the other end we have the largest defects. What about the diffuse defect? This is the average normal defect. The range is +5 up or +5 below the normal range. So the diffuse defect, it's a parallel downward shift of the defect curve. This is the normal defect curve, and this is a downshift of that curve. The diffuse defect is calculated from the magnitude of downward shift of the defective curve at the rank from 20th to the 27th percentile. For the G pattern, it is located between the 12 and 16 location of these 59 points. An estimation of the depth of the diffused effect that's at this zone is written down. In this example, there is no deviation because the curve of the patient is inside the normal range. In this example, the diffused effect estimated to be 2.6. Here there is no defect, deviation is 0. Here also 0. Here the deviation, diffused deviation is more. It is 7 decibels. In this example, the diffused effect was found to be 4.5 decibels. So all these deviations from the normal, we took out of them 4.5. So this point was, when compared with the normal, was found to be 10, but here was found to be only 5. Again, this point 22, here it is 16, and so on. As you notice here in the octopus, they usually write a number. They don't write minus 9, minus 15 like the Humphrey do. Just write the differences, and we understand that this difference means that these values are different from the normal with such a value. So the differences here is 10 before correction, but after correction it became 5, and so on. Let's see this example. This patient was found to have a diffused effect of a value of 5 decibels. In comparison table, a point was found to be 12 decibels below normal. These 12 decibels, 5 of them due to media opacity or generalized depression, and the actual local changes amounts to the remaining 7. So as you notice, both the Humphrey and octopus make correction to get rid of the media opacity or the generalized depression, but with different mechanisms. The Humphrey depends on arranging data from the highest to the lowest, and then software go to the location 85%, or we can say the 85 percentile location, and any difference is used to be adjusted compared to the normal, and we add or subtract values to the patient. In case of octopus, the data are arranged from the smallest defect to the largest defect. That's to mean the highest sensitivity here and the lowest sensitivity there. Then the software go to this location. This is between the zone between the 20th to the 27th percentile. And this is used to adjust the data of the comparison table into the corrected comparison table. So the Humphrey uses a zone 15th percentile from the top, while on the other hand the octopus use a value of around 24-25 percentile from the top. But the idea is the same, to correct or to get rid of the media opacity.